So let's just talk about a few problems, and I'll build up the rules of radicals as we go. There are rules you have to follow. You can't just wing this stuff. Just like with fractions, you have to be very cautious about everything. So let's start with number 8, which is the square root of 25 plus the square root of 49. Now, when you say the square root of 25, you all should know the answer is 5. And the square root of 49, you know the answer is? But why?
Because 5 times itself is 25.
Because 5 times itself is 25. So one of the rules, we'll just be putting these throughout, so put little boxes around these. One of the rules is if you have the square root of something squared, it's equal to that something. Would you agree with that?
Yeah.
Really?
Yeah.
Okay. So, what's that?
Someone said it like that, but I agree.
If you square a number and you take its square root, you get the number back, right?
Not necessarily.
Not necessarily. What kind of number wouldn't work? Negative.
A negative is the
If you have the square root of negative 3 squared, the answer is 9, and the square root of 9 is 3. So you have to be really careful. When you say the square root of n squared is equal to n, that's only if n is greater than or equal to 0. That rule does not work if n is less than 0. If it is less than 0, you have to change its sign. Since we haven't talked about it, it's the absolute value of n, but we've never talked about absolute value.
I'll ask you. Well, I'll ask you. Since I argued the practice problem, it was confusing to me because it's like the very first one is saying that if the radicand is negative and the index is an even number, it has no solution. Why is that?
Because if you think about this rule, it's the same number multiplied by itself. And are you talking about inside?
Yeah.
Like the square root of a negative 4?
Yeah, like
something
if
like
we
that.
had like negative 64 and the radicand was 4, and it was like,
All right.
there's no
So,
solution.
square root of negative 4, right? Now this whole idea is the number that goes on the inside has to be itself times itself, right? So what two numbers multiplied together give you negative 4?
2.
2 and 2 is positive 4.
Oh.
Negative 2 and negative 2 is positive 4. So you're kind of stuck with this one going, I have no idea. What two numbers multiplied to give you negative 4? Because they have to be exactly the same. So this doesn't work. This is, the best we can say is not real. There are no real numbers such that this works. Now that kind of leads into, are there numbers that actually do work? Yeah. So one of the rules is you have to be really careful about the sign on the inside and the sign on the outside. Making n positive all the time, this is called a principal root. When you take the square root, a 4th root, a 6th root, an 8th root, an even root of a number, you're always going to end up with what's called a principal solution, the positive solution. You'll never have the square root or a 4th root or a 6th root equal to a negative answer. So not only can you not take the square root of a negative number, the answer is also not going to be negative. Okay, so that's just considered a principal root. The answer has to be positive. Okay. So there's a lot of little pieces you have to be very cautious about, and it depends a lot on what kind of root you're taking or what kind of radicand you're dealing with. All right, so the square root of 25 is 5, the square root of 49 is 7, and 5 plus 7 is 12. Okay. What about the square root of 25 plus 49? Would it be 12 also? You think? Let's,
No.
do you remember what this bar means? No, what's this bar mean? When you have a long bar, what's it represent? Parentheses. And if there's parentheses here, what do you have to do first? Inside the parentheses. And 25 plus 49 is? 74. 74. So this would be the square root of 74. And the square root of 74 is definitely not equal to 12. Because the square root of 144 is equal to 12. So there's some subtle rule going on here. The square root does not distribute, now I say the word very loosely, distribute over a sum. Over a sum. It actually follows the laws of exponents rather than any other weird laws. Good morning. All right, so be really careful. It has to be a square root plus a square root that you can do the square roots individually and then add the answers together. If it's a square root of a sum, you have to do the sum first. And the only reason I showed this bottom one is because I've seen people do this. And my college algebra class really wants to do it because it would simplify life a real lot. But you can't do that. That's illegal. So this is definitely not equal to x plus y. So you got to be very, very cautious. They have to be products underneath. All right, let's try another problem and see what other little quirks come up with square roots. Number 10. The negative square root of 4/25. Now, is this the same thing as taking the square root of negative 4/25? No. That negative has nothing to do with taking the square root. Basically, it's just saying whatever the answer is, it's going to be negative. That's all it's saying. So what number can you multiply together to give you exactly the same number to give you 4/25? 2/5. So the answer is going to be negative from the negative out front, 2/5. Now, if you think about that, what's the square root of 4? Square root of 25. So basically, I took the square root and separated it top and bottom, but that's next section when we start talking about that. But that's the general idea. But here, we're looking at 2/5 times 2/5. So we're thinking of it this way. 2/5 times 2/5 is 4/25. And therefore, the square root of 4/25 is 2/5. That's the way we're looking at it right now. Number 14. These are little baby problems. The square root of 0.16. The square root of 0.16. It's got a 4 in it, that's for sure, because you know that 4 times 4 is 16. What kind of 4?
4 tenths.
4/10. Oh, I didn't hear the tenths part. I usually just say 0.4, so 4/10. Because 0.4 times 0.4 is 0.16. So those are just little simple ones. We can also create a function out of this. We can say, number 16. We have this function f of x. Y'all have your calculators, right?
No.
You're going to need them. You don't have a calculator in math?
I lost it.
You lost it? Oh no. Square root of 10x plus 5. And the first thing they want to know, you don't need a calculator for the first one, I hope. F of 0. Well, we probably do. How do I find f of 0? Plug in 0 for x. Before you do the plugging in, though, I highly suggest you go 10 parentheses plus 5. It'll help you out when you start dealing with functions a little bit more in college algebra to do that step first, and then plug in whatever is inside these parentheses over here where the function is. So what goes inside the parentheses is what goes inside those parentheses, which is 0. 10 times 0? What property? Oh, you don't know what property that one is. But 0 plus 5? What property?
Additive.
Additive identity. So this becomes
5. 2.5.
okay. 10 times 0 is 0. 0 plus 5 is 5. You're forgetting this thing? Square root of 5, which is approximate. When you type it in a calculator, you're getting an approximation. It's somewhere bigger than 1, and, well, actually, somewhat bigger than 2, but smaller than 3. 2.24? That's good. 2.24. Since we put that little squiggly approximation in there. So what happens with functions is, square root of 5, this is considered an exact answer, where 2.24 is considered an approximate answer. Now, if you're doing more calculations with this value, which one's better to use? No, the square root of 5. You want the exact answer in further calculation so you don't get what's called rounding error, because that's not exactly equal to the square root of 5. So as long as you can keep exact answers in your work, your rounding error is going to be very small and usually occurs at the very, very end. If you use 2.24 in all your calculations after this one, it'll mess it up every time you use it, just a little bit, and eventually they kind of accumulate to be bad errors, critical errors. How about f of 1? Well, f of 1, you just plug it in. You go 10 times something plus 5. What's the something? 1. And 10 times 1 is 10. 10 plus 5 is 15. So this becomes the square root of 15, which is approximately. Now the square root of 16 is 4, so this should be just a little shy of 4. 3.87. If you can find a perfect square root that's close to it, you can at least get an approximate idea of what it's equal to. Doesn't always work, but you can get a good feel for some of these numbers. F of 2. So let's see here. The square root of 10 times 2 plus 5. And this one's nice. What do we get? You get 5 out of it. It's the square root of 25, and this is exactly equal to 5. Identical to 5. All right, square, how far does it go? Square root of, well, f of 3. So f of 3 equals the square root of 10 times something plus 5. That something happens to be 3. 10 times 3 is 30. 30 plus 5 is 35. So this is equal to the square root of 35. What's 35 close to as a perfect square? 36. So the answer should be somewhere around 6, a little bit shy. 5.91. That's really close. 5.91. Okay. Now, basically what we have just created is a table of values. And if you have a table of values, you can graph. So instead of doing the one I was going to do, which is number 20, let's just graph this one. We have all the values listed out for us. So if we do just a quick sketch of a graph, I don't need to go to the left because there's no negative values. We have 0, we have 1, we have 2, and we have 3. I'm curious. Well, we can talk about that later. So let's see here. We have 1, 2, 3 on the x-axis. And we have, say, 0 to 6 on the y-axis. So 1, 2, 3, 4, 5, 6. We can just approximate graph it. All right? That's horrible. My axes are all crooked, but no, life goes on. So the first coordinate we're going to graph is 0, 2.24. So where do I go?
Straight up 2.24.
Straight up 2.24. And you're just doing an approximation, so plot it somewhere between 2 and 3. Closer to a half than anything else. Next one is 1 and really close to 4. So 1, a little bit shy of 4. Right about there. The next one is 2, 5, so you go over 2 and up 5. And the next one is 3, really close to 6. Now here's my question of the day. When does this function equal 0? In other words, I need to create a square root of 0 up here. So what value of x makes this equal to 0? Well, 10x plus 5 is equal to 0. How do you solve it? If you have 10x, you want to know when this is equal to 0, so set it equal to 0. When's 10x plus 5 equal to 0? Negative 1/2. So if we come back over here, and this is negative 1, then the graph is starting here, at negative 1/2. At negative 1/2, you get 0. So if I did f of negative 1/2, I would get the answer of 0. Because negative 1/2 times 10 is negative 5. Negative 5 plus 5 is 0. So you get negative 1/2, 0. So the graph of this thing starts here. It goes that way. Can I plug in negative 1? We can try. Let's do it. F of negative 1 would equal the square root of 10 times negative 1 plus 5. What's 10 times negative 1?
Negative 10.
Negative 10 plus 5.
Negative 5.
Can I take the square root of negative 5?
No.
No, not real. So there are no points to the left of negative 1/2. This graph starts at negative 1/2 and goes off to the right. Never ever goes anywhere to the left of negative 1/2, which is kind of weird. Because we're used to graphs going off in both directions. But it's that idea of principal root. The answer has to be positive and the number underneath has to be positive. Alright. So that's the warm-up part. So what about cube roots? Number 26. Is there any difference between a cube root and a square root? And I'll start off with the one big difference that they have. Now, technically, we've already done this. You'll recognize it in a second. This is saying what three numbers, the index here, what three numbers multiply together to give you a negative 125, which would be negative 5, because if you have negative 5 times negative 5 times negative 5, negative times a negative is a, times another negative is a negative. And then 5 times 5 times 5 is 125. So when you take the cube root of a negative number, you actually get an answer. Whereas a square root of a negative number doesn't give you any answer in the real number system. So the cube root of negative 125 is negative 5. It's just negative 5. All right. So cube roots, you don't have to worry about positives and negatives. The inside could be negative, the answer could be negative, you don't care. So odd ones you're not really worried about. Those even ones that'll cause us trouble. How about 36? Similar to one of the ones earlier. Cube root of negative 8/27.
2/3, negative 2/3.
Negative 2/3. So this would equal negative 2/3. Because 2/3 times 2/3 times 2/3 would be 8/27. And the negative kind of just carries along with it. So the cube root of a positive number will be positive. The cube root of a negative number will be negative. Guaranteed. All right. How about, this is a little bit more important. The relationship between radicals and rational exponents. Now, in 7.1, when we had something like 27 raised to the 1/3 power, 27 raised to the 1/3 power, I showed you to take care of that 27 and make it something raised to the 3rd power. So this becomes something raised to the 3rd power. What is that something? 3. And then you're going to take it and raise it to the 1/3 power. And the reason we did this is so that the 3 times 1/3, because power to a power you multiply, the 3 times 1/3 becomes 1, and 3 to the 1st power is 3. But that's the same thing as doing the cube root of 27, because the cube root of 27 is also known as 3. Because the cube root of 3 cubed, the 3's basically kind of cancel out, you get the 3. So what I'm trying to say here is that if you have the square root of a, we can also write this as a raised to the 1/2. If we have the cube root of a, we can write that as a to the 1/3. If we have the 4th root of a, which you have to be careful, a is positive and the answer is also positive. It's an even root, you have to be positive all the way around. That's an a, not a 9. So the 4th root of a is also known as a to the 1/4. So therefore, if I just put a n up there, whatever number I want, it has to be a whole number. It can't be negative. The nth root of a would equal a to the 1n. This one you have to be careful with. That one you have to be a little careful with. So let me write it down again. So if you have the nth root of a, it's equal to a to the 1n. If n is odd, a is any real number. Oh, by the way, that little symbol there, you might as well get used to it. It's a double bar R, it represents real numbers. If n is even, then a and the nth root of a are positive. Principal root, principal answer. So if n is odd, we could care less. Both of them could be negative, the answer and the number underneath. But if n is even, the inside has to be positive and the outside has to be positive. You can't have negatives anywhere. Now that's not saying that I can't have something like the negative square root of 4. Negative square root of 4 is just equal to negative 2, which is perfectly fine because it's not the square root whose answer is negative, it's just this expression's answer is negative. So this is perfectly safe. But you cannot take the square root of negative 4. And you can't say the square root of 4 is equal to negative 2. Neither of those is going to work. So just be a little cautious. All right. So with that nice little rule, we can do some simplification of radicals using rational exponents. For instance, number 40. The sixth root of a to the fifth. And what we're going to do is we're going to write it as a rational exponent. In other words, something raised to a power. In this case, a raised to some power. Now, what does the sixth root of something represent as a rational exponent? 1/6. So this becomes a to the 1/6, all raised to the fifth. So that fifth power is still sitting outside. What happens when you have a power to a power? You what? You multiply. So this becomes a to the, what's 1/6 times 5? What is it? 5/6. So you get 5/6. Isn't that easy? Not much to it. Number 44, something that just looks ugly. The ninth root of a minus b raised to the fifth. I forgot to say something about this. A little number in the nook here, this thing, this 9 and this 6 up here, these are called indexes.
I always thought it was a cranny.
It's a little cranny, yeah, nook and cranny. If you forget your index, you're automatically saying it's a square root. What's the index of a square root? 2, but you don't write it. It's just understood. But if you forget to write your index, you're actually changing the answer because the square root of 8 and the cube root of 8 are two different numbers. Square root of 8 is like, it's close to 3, where the cube root of 8 is 2. So they're different values. All right, what's the 9 as an index represent as a rational exponent? 1/9. So you're going to get a minus b raised to the fifth power raised to the 1/9 power. There's an obvious shortcut here, but I don't want to talk about it. I want to write it out so you can see where all these things are coming together. And again, here's power to a power. So 5 times 1/9 is 5/9. So we get a minus b raised to the 5/9. Is that the same as a to the 5/9 minus b to the 5/9?
So it don't matter like which order you put in.
Well, this one, oh, I pushed the 5 out, yeah. No, technically it doesn't because multiplication is commutative. But yeah, I should have wrote this one, a to the 5th raised to the 1/6. I was thinking it was, in my brain, Yeah, my dyslexia just kicked in. But this is definitely not equal to a to the whatever minus b to the whatever. That doesn't make any sense. I talked about this earlier. Didn't I? I thought I did. I did. Let's go back to polynomials for a second. If you go back to polynomials, there was this problem. If you have x plus y raised to the second power, is that equal to x squared plus y squared? No. Because this power cannot distribute over a plus sign. So you, well, distribute. It's really not the distributive property. It's one of the exponential laws. But you can't do it when there's a plus sign here. This is equal to x plus y times x plus y. Because you can't do it with a 2, you definitely cannot do it with 5 nines. If it doesn't work for an easier case, it's not going to work for a harder case. It has to work for both of them. So that's your answer. Don't change it. This is what you get. This is what you leave it as. Don't be thinking distributive. Now, if it was 5 nines times a minus b, right? Can I think distributive? Yeah, because that's a distributive property. This doesn't have a distributive property. This is not a number. This is a exponent. You don't treat them the same as numbers. They get treated a lot different. I know someone's going to do it anyway, so. How about, no, that was boring. Trick question, number 50. The fifth root of negative 11 raised to the fifth power. It's going to be negative 11? You sure? No.
Remember this root?
Well, you could use it by rule, or you could use it by changing it into a rational exponent. This becomes negative 11 raised to the fifth. The index on the thing is a 5, so that becomes 1/5. And 5 times 1/5 is 1, and the answer is negative 11. They kind of cancel each other out, but you better be careful. You better be careful. For instance, this isn't in the book. The fourth root of negative 7 raised to the fourth power. Well, let me just do it underneath. So if I change this one into a rational, we get negative 7 raised to the fourth, and then the whole thing is raised to the 1/4. So what's the answer? It can't be, because it's even. It has to be positive. The answer to this is 7. So don't go thinking all the time that they just cancel. That's the danger of canceling. Yes, 5 times 1/5 is 1, and the answer over here is negative 11. But it's negative 11 because the index is odd. Here we have an even index, and I've been talking about this. The answer on the inside has to be negative, and the answer on the outside, the number on the inside has to be positive, and the answer also has to be positive. So even though this is negative 7 on the inside, you have to change it for even ones.
That's only if it's raised to something on the inside.
Only if it has
It's a positive number.
an even index. If it's an even index, the answer is always positive.
I'm talking about like this raised negative 7 to the 4th.
Right.
And then you got the 4 right there. Is that the only time you do that? Because if it's negative, like you're just doing the 4th root of negative 64, then that's the imaginary number.
Right.
Yes,
Well, yeah, but see, if I raise negative 7 to the 4th power, it's positive. That's a positive number.
This is the only time that I can do that with the negative.
You got to be thinking, hold on. I said if you're taking an even root, this is even, the number in here has to be positive, and the answer also has to be positive. Now, is this number negative? No. On the inside, it's not negative, because negative 7 times negative 7 times negative 7 times negative 7 is a positive number. You're just not writing it out as itself. You're just looking at it as negative 7 to the 4th. But that is a positive number, so when I pop it out, it also has to be positive. But the whole idea is the number on the inside has to be positive, and so does your answer, no matter what. If the root is even. If the root is even. Let's do one more, just to really mess you up. The 7th root of negative 3 to the 7th power equals? Negative 3. The 6th root of negative 4 to the 6th power? 4. Is positive 4. If it is even, you have to make the answer positive. Now that's not saying that the 6th root of -4 raised to the 6th power. What's the difference between these two? The parentheses. Where this number, if you multiply it out 4 times or 6 times, this is a positive number. If you raise 4 to the 6, you're going to get a positive number, but sitting in front is a negative. This is not real. Because you cannot take the square root of a negative number. You see the distinction? Okay. But that's the big thing. So if it's odd, you could care less. If it's even, you've got to be very careful. You've got to be very, very careful. Because everything has to be positive. The danger of this is sometimes it's very easy to do, and since it's easy to do, you don't think about it too much, and sometimes you want to think about it a little bit more than you want to. How about if we just go backwards? Number 58. What if we started with x to the 5/6, and I want to change it into radical form? Where these over here, pretty much I was changing radical form into rational form. I want to go backwards, rational form into radical form. One way of looking at this is kind of how we separated it in 7-1. The 6 represents what? 1/6, right? We would change it to 1/6 and 5. So if you want, you can change this into x to the 5th raised to the 1/6. Or you could change it to x to the 1/6 raised to the 5th. It doesn't matter because multiplication is commutative. All right, so what's the 1/6 power represent? The index, so we get a radical. The index is 6. Inside is x to the 5th, which is exactly the same as the 6th root of x, all raised to the 5th. Either one is acceptable. Now, be careful. The computer probably only accepts the first one. But for my purposes, like on a written test, I don't care which way you write it. But this is technically, the first one is technically the simplified version. If you do this in the computer, I don't think it'll let you say it's the right answer. I think they want this one. They want that one. Because it's actually simpler, because it doesn't have parentheses. Anytime you can write an expression without parentheses, without doing a lot of extra work, it's better. All right, that's not too bad. How about simplifying with rational exponents? There's a lot of little pieces to this one. For instance, 82. The cube root of -27 x to the 9th. The cube root of the cube root of -27 x to the 9th. Highly suggest that you change this into an exponent because you know your exponential laws. I haven't shown you your radical laws yet. So how can I deal with this 3? It's a 1/3 power, so you take the entire, remember this line needs parentheses. So you take the entire inside and you put it in parentheses, and you raise it to the 1/3 power. All right, now we can use the laws of exponents. I have these two things multiplied together on the inside, and it's all being raised to the 1/3 power. This is where you get that idea of distributive, and I'd rather you not even think of it. This becomes -27 raised to the 1/3 power times x to the 9th raised to the 1/3 power. Oh my God. You write this over. -27 1/3 times x to the 9th. That was weird. So, what's -27 to the 1/3 power? -3. It's -3. What is x to the 9th to the 1/3 power? X to the 3rd. X cubed. So there's your answer. And that's the best way to simplify it in pieces so you don't have to do it all at once. Because if you do it all at once, things get a little confusing sometimes. How about 86? Which will give us another rule. So put a star by this one. This is the one that gets people. It looks easy, and then you have to think about it. The fourth root of a to the fourth b to the 20th. The fourth root of a to the fourth b to the 20th. Okay. So if we change the fourth root into its power, it would become 1/4. That goes on the outside as an exponent. And then on the inside is still a to the fourth and b to the 20th. Okay. A to the fourth raised to the fourth. A to the fourth raised to the fourth times b to the 20th raised to the fourth power. So the first one is a. The second one is b to the fifth. I disagree.
Why?
What's the cautionary tale on this one? What was the index here? 3. What do I not care about? Negatives and or positives. What's the index here? 4. Are they? A is a variable. A can represent anything. Negative numbers and or positive. Now again, this lands into an area that we didn't cover in the beginning of the class, but there is a way of dealing with this. So there's a reason for the star. There's a major rule that you need to know. Star, star. If you take the square root of x squared, the answer has to be positive, but x can be positive and or negative. The real answer is the absolute value of x. What's the absolute value do to any number? Makes it positive. So even if the answer is negative, the value of x is negative, putting absolute values around it forces it to be positive. And if it was positive to begin with, it doesn't change a thing. So this is really important. Now generally, most math teachers will say, well, let's just assume that all variables are positive, then you can drop the absolute values. But for this book, they don't assume that. When you get to college algebra, we assume it for a little while, just to make life easy. But again, we have to come back to the square root of x squared is equal to the absolute value of x. So the technical answer here is the absolute value of the product. To make sure that a times b to the fifth power is positive. Let me change the problem up just a little bit. What if I had fourth root of a to the 8th, b to the 16th? The fourth root of a to the 8th, b to the 16th. Well, it starts off exactly the same. You get a to the 8th, b to the 16th, raised to the 1/4 power. Right? We put a little box here, separate it away. And then when you go a to the 8th raised to the 1/4 power, you get a to the second. And b to the 16th raised to the 1/4 power becomes b to the... Do I need absolute values here?
Yes.
No.
What?
Why?
You got two positive numbers.
I have two...
Positive exponents.
No. What's true about the exponents?
They're all positives.
They're even. And if you raise something to an even exponent, whether it's positive and or negative, the answer is always going to be positive. You don't need them here. I know, isn't that crazy? That's why in college algebra I say, let's just assume all variables are positive, then we don't have to worry about it. But it is true that if the exponents are odd, you have to put absolute values on it if the index was even. But if the exponents are even, you can ignore it because it forces it all to be positive anyway.
But did we need to worry about it on these things, did we?
What's
Oh,
that?
because the answer, because it's in the answer, it has to be the absolute values. On the 86?
This one
Yeah, since the b to the 5th,
is odd.
that means that we have, it's the answer, not the actual question being asked.
Okay, I'm confused what you're saying.
That's the
I
answer,
understand
never
what
mind,
you're
I got you.
You got, I don't even got me now. All I'm saying is If you start off with an even index and you end up with variables with odd powers, you have to put it around absolute values. If you start off with an even index and you end up with even powers, you can ignore it. You could put them, but that's not the simplified version. The simplified version is really a to the squared b fourth.
So what happens if you have an index of odd?
Good question. That one I can handle. And this is probably one of the trickier parts of the whole thing. What if we had an even and odd situation? So the sixth root of x to the 12, y to the 18. What if we had an even odd situation? Now, sixth root, we have to make sure all our answers are positive. So we set it up and we get x to the 12th, y to the 18th, raised to the 6th power. Ooh, 1/6 power. 1/6 power. All right. X to the 12th to the 1/6. X squared. Y to the 18th to the 1/6 power. Y cubed. Now, x squared is going to be positive one way or the other, but y cubed might be negative. The absolute value is still there.